In the last Pencast, we learned the fundamental theorem of calculus, actually part 2 of the fundamental theorem of calculus. There's a part 1 also. And part 2 is on page 396 of section 5.3. And it says, if f is continuous on the closed interval a, b, we're really only dealing with continuous functions here, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a, where f is any antiderivative of little f. In other words, you find an antiderivative of little f, evaluate it at the endpoints, and subtract. Now, it says any antiderivative. You may have wondered in our previous Pencast, when we evaluated the definite integral from 0 to 2 of x squared dx, I put an antiderivative was x cubed over 3. That's true. The most general antiderivative is x cubed over 3 plus c. But notice fundamental theorem calculus says you can use any antiderivative here. So I just use the one with c being 0. Notice if we put a plus c here, right here, and we put a plus c here, right here, we would be subtracting those c's and they would disappear. That's why any antiderivative works. You'll also recall that I wrote the notation for evaluating an antiderivative at the endpoints like this in the previous Pencast. But we normally shorten that to, this piece right here. This piece right here. We normally shorten that to this. We say x equal 2, or 0, x equal 2. Sometimes we write it like this. You know, we either write a vertical bar there or a right-hand brace or the whole braces. That means that's 2 cubed over 3 minus 0 cubed over 3. This is just shorter notation than that. So I get 8/3. Now, this fundamental theorem of calculus should surprise you. Okay? It's not at all obvious. Think about it. What does area under a curve, what does sum of areas of rectangles have to do with an antiderivative? A derivative gives you a slope of a tangent line. The antiderivative goes backwards on that. Yet, these two are fundamentally connected some way by the fundamental theorem of calculus. What's going on there? That's not obvious at all. Now, in section 5.3, there's a formal proof of the fundamental theorem of calculus. And if you're interested, I encourage you, especially your math majors or people taking Cal 2, I would encourage you to look at that. But we can get a glimmer, all of us can get a glimmer of the fact that even though this at first seems like a surprising result, we can get a glimmer of why it might be reasonable if we look at a practical application. In section 5.1, they talk about areas and distances. Before the next Pencast, I want you to look at these two questions, and I want you to try to answer them. We'll come back in the next Pencast and give the answers. You can check your work. And this, when we think about it for a minute, the answers to these two questions will provide some insight for us and make it seem more reasonable that the fundamental theorem of calculus would work. So what are the questions? If you start 2 feet in front of the CBR, in other words, your position at time 0 is 2, S of 0 is 2, and when we start the clock, you walk away from the CBR at a constant speed of 3 feet per second, what is your position after 6 seconds? That is, what's the value of S of 6? You can answer this easily without calculus, okay? This is an easy question. And then, how far did you travel in these 6 seconds? In other words, what's the value of S of 6 minus S of 0? Are these two questions asking the same thing, or are they slightly different? The other question is, for this scenario above, in other words, you start 2 feet in front of the CBR, we turn the timer on, you walk away from the CBR at a constant speed of 3 feet per second. You do that for 6 seconds. Draw the graph of the velocity function. And I want you to find the area of the region between this graph of the velocity function and the horizontal axis on the interval of t's or x's or whatever you want to call the inputs going from 0 to 6. So you really need for you to do this. Every one of you, if you think, can get the answers to this right. Compare your answers to these 2 bullet points, and then we'll come back, check our work, talk about what this means for the fundamental theorem of calculus.